Hey, welcome to this problem-solving session where we are going to be focusing on addition reactions from Chapter 8 of your Wade textbook. So we will jump right into the problems. Remember that these problems are available to you on Canvas. If you go under Files, you'll be able to download a blank copy of this, and I highly recommend that you give these problems a try before you go through this solution video, and when you run into problems or stumbling blocks, come in and take a look at the solution video for a particular problem. So we're going to start here with question number 1 in this particular video, and then there will be additional videos for the other questions, questions 2 through 4. So question 1, predict the major organic products of the following reactions. We have pent-1-ene reacting with HBr. So what I'm going to do to start this problem is draw out our structure of pent-1-ene. The 1-ene indicates there needs to be an alkene group starting at carbon 1. Pent there indicates the carbon chain is 5 carbons in length. So we're going to draw our 5-carbon chain in here. And then we're going to react it with hydrobromic acid, HBr. And in order to ensure that I'm getting toward the right product here, I'm going to sketch out at least part of the mechanism for this problem. So anytime you're reacting an organic molecule with a relatively strong acid, such as HBr that we have here, the first step is always going to be protonation, where the organic molecule is going to use its lone pair of electrons or a pi bond to pick up a proton from the acid. So we have our pi bond over here, comes over, grabs that proton from the acid. That forces the bond between H and Br to break. And then that will give us, as our product here, a molecule that still has a 5-carbon chain. Now the proton that we just attacked, that I'm showing in green there, has to go onto one of the 2 carbon atoms of the alkene group, here or here, highlighted in green. So it's going to go to one of these 2 spots. And the way you decide which of those places to put the new proton is you follow Markovnikov's rule. And I'm just going to abbreviate that as Mark's rule. You'll want to always remember to follow that. And Mark's rule says that you are going to attach the proton to the less alkyl substituted carbon of that alkene group. In other words, the other way that you could say this is, rather than bonding the proton to the less alkyl substituted carbon, the alkyl is going to bond, the hydrogen is going to bond to the carbon with more directly bonded hydrogens. Because the carbon that has more directly bonded hydrogens will always correspond to the less alkyl substituted carbon. So what that means is that when we decide where to put that proton in, that proton is going to go right here. So we started off with CH2. We picked up that green proton right here. And now we have CH3 there. Don't forget that the other carbon atom that was originally part of that alkene group now has to be a carbocation, because it no longer has a double bond, it just has a single bond. And so that means that particular carbon atom has only 3 covalent bonds in total, because it's a CH group there, and therefore it is going to be a carbocation. That carbocation is very, very electrophilic. It is very eager to have a nucleophile come in and attack it. And it just so happens that this first step of the mechanism, in addition to generating our carbocation, also generated bromide anion. So now we have a reaction mixture that has both a nucleophilic bromide and an electrophilic carbocation. Match made in heaven there. You do want to always check when you create a carbocation. If you have created a secondary carbocation, you always want to ask yourself, is there a way to do a 1-2 shift, also known as a carbocation rearrangement, in order to convert that secondary carbocation into a tertiary carbocation? And in this case, we do have a secondary carbocation here in the middle of the screen, but there's no way to do a shift of a hydrogen or a methyl group in order to create a tertiary carbocation. So that carbocation is going to stay as is, no carbocation rearrangement in this particular reaction mechanism. And so what's going to happen here, just sketching out at least part of the mechanism, to help us get to the right final answer here. The bromide anion comes in, attacks the positively charged carbocation, and that's going to give us our final product here. Like so. Now you might be wondering, we do have a chiral carbon in our final product here. That carbon right there is a stereocenter. And so you may be asking about what the stereochemistry is going to be at that chiral center. And the answer is that if we were showing stereochemistry here, we would be creating a mixture of the R and the S enantiomers of this, because when we have our carbocation reacting, the carbocation is reacting right here in the middle of the screen. That carbocation is trigonal planar in shape. It's laying completely flat. And so therefore, there's no preference for the bromine to attack from the top of the molecule or for it to attack from the bottom face of the molecule. And attack from those two different directions will lead to the two different stereochemistries here, the two different configurations. So we will actually create both of these two molecules that are related as enantiomers. One where we have the wedge going to the bromine, the other where we have a dash going to the bromine, and those will be our two major final organic products of this reaction. So I'm going to go ahead and put a box around those to remind you those are our final major products. And if you were given this question on an exam or something like that, all you would need to put would be the final answer here, because it's just asking you in the question to predict the major organic products. It didn't specifically ask for a mechanism, but my strategy for solving problems is that if I know the mechanism for a reaction, I try to sketch out at least the key parts of it to enable me to be confident that I have predicted the right product, because it's awfully easy in going through these to forget a step such as a carbocation rearrangement or something like that. So I like to have at least a little bit of the details in there showing my work about how I got from beginning to end to get the reaction correct. All right, so let's go on to the next problem here, which we're going to solve analogously to part A. So here we have 3-methyl-cyclohexene. Remember that word cyclo in there is really important. I commonly see people make a mistake where they'll be given something like this and they forget to put the ring in. They just draw a chain. So be sure that you're paying attention to the fact that there's the word cyclo in there. So 3-methyl-cyclohexene implies that our alkene group has to be between carbon 1 and 2, because when we are drawing alkenes, it's always going to be the case that the alkene group takes priority for deciding where to start numbering the ring over the alkyl group, the methyl group here. And so position 1 is going to be the first carbon of the alkene group. Position 2 is coming on into the alkene group, and then we come on to position 3 where there is a methyl. And it doesn't specify the configuration of this stereocenter at position 3, so we'll just leave it as a line indicating we don't know what the configuration of that stereocenter is, and that's okay. So then we react with HCl. Much like above, I'm going to sketch out a bit of the mechanistic detail of this to make sure that I'm on the right track to get the correct product. So we'll go ahead and protonate there. That breaks the hydrogen-chlorine bond. And then we'll go ahead from there. And in this case, positions 1 and 2 are equally favored to pick up the proton, because each of those positions, positions 1 and position 2, are equally substituted with alkyl groups. So we're going to create two different isomeric carbocation intermediates here, one that will have the positive formal charge here, corresponding to our newly picked up proton going on up here, so we'd have CH2 up top here. And then the other carbocation intermediate would correspond instead to the positive charge going right here. And that would correspond to the proton having been picked up on this carbon atom. So now we look at these two and we ask ourselves the key question. In each of those cases, is it possible to do a 1-2 shift in order to transform either of these secondary carbocations into tertiary carbocations? And the answer to that for the one on the left here is yes, we can do a 1-2 shift. And doing that 1-2 shift, what we would need to do here is we keep in mind that we are moving a methyl group or a hydrogen by one position in order to move that positive charge from a secondary carbon so that it is then a tertiary carbon that has the positive charge. So if we move the hydride over, that hydrogen there that I'm showing in black, if that comes over, that is going to enable the positive formal charge to move to the tertiary carbon position. So let's show that now. Once we move that hydride over, then we would have a CH2 group right here. And now our plus charge would move to right here because now that position at the bottom here at the 6 o'clock position is where we would have a deficiency of bonds. So now at this point, sailing along analogously to up top, where we'd have our chloride anion that we generated as a result of the first step of the mechanism comes in, acts as a nucleophile to attack the carbocation there. Similarly, down here, chloride acts as a nucleophile to attack this tertiary carbocation, and that's going to lead us to our final product here. So we'll have a chlorine bonded there as one of our organic products of this reaction. The other going to have a chlorine up here. And I'll go ahead and put a box around each of those products. So we got one of our products here. The other one is this. These two are related as constitutional isomers, going back to the vocab related to the relationships between different molecules. So with that, we wrap up question number one of the key skills here being that when you're given a couple of reactants, you should be able to walk through predicting the final organic products of these reactions. In the next couple of videos, we will tackle some additional reaction types that we are learning about here in chapter